Hi, welcome to this lesson on trigonometry, trig identities part 2. Let's have a look at question 6. Okay, so I'm going to focus on the restrictions first, and immediately on the left-hand side, I see a tan alpha. So when is tan alpha undefined? When does it have restrictions? At its asymptotes. So the asymptotes are when alpha is 90 degrees plus the period of tan, which is 180 degrees times integer k. So therefore, if I put k equals 0 here, then alpha is 90 degrees. If I put k equals 1 here, alpha is 270 degrees. And any other k integer value is going to be outside this domain. Okay, so there are the two restrictions. Alpha cannot equal 90 degrees. Alpha cannot equal 270 degrees. The same thing can be said for the right-hand side. You have a denominator of cos 2 alpha plus 1. If that's equal to 0, then that fraction becomes division by 0, which is undefined. So this becomes cos 2 alpha equals -1. Okay, so we're solving a trigonometric equation. Let's get the cast diagram ready. Now, cos is negative in the second and third quadrants, and the reference angle is going to be cos inverse of +1, always the positive. So that is at 0 degrees. So therefore, in the second quadrant, you have the angle 2 alpha must be 180 degrees minus the reference. So 180 degrees minus 0 plus k times 360. And if you divide both sides by 2, you get alpha equals 90 degrees plus k times 180. And that's exactly this first restriction we had on the left-hand side. So we get the same answers there. And in the third quadrant, we have 2 alpha equals 180 degrees plus the reference angle. So you get exactly the same equation again. Alright, so those are all the restricted values. So now let's go ahead and start the proof. Okay, so to prove, looking at both sides, I think the right-hand side looks more complex. Just as a nice little side observation, we know that tan alpha is sine alpha over cos alpha by the quotient identity. That almost looks like it's the case here because there's a sine 2 alpha over cos 2 alpha, but there's this little +1 added. So that's a nice little observation here. Okay, so the proof, I'm going to start with the right-hand side as that is the more complex looking side. So it's sine 2 alpha all over cos 2 alpha plus 1. Okay, now sine 2 alpha is a double angle identity. So sine 2 times an angle is 2 times sine the angle, cos the angle, all divided by. Now I need to pick one of the three variations for cos 2 alpha. That'll help me in this expression. Now there's a +1 here. If I can get rid of that +1, it would be great. So I know that the three variations for cos of 2x is cos squared x minus sine squared x, 2 cos squared x minus 1, and 1 minus 2 sine squared x. So I'm going to pick the second one because it's got a -1 there. So I'm going to say 2 cos squared x minus 1 for cos 2 alpha, sorry, cos 2 squared alpha. Okay, keep the angles consistent, plus 1. So now I have 2 sine alpha cos alpha all over. So the -1 plus 1 will cancel to 0, and you're left with 2 cos squared alpha. So now everything's multiplication. You can divide the 2's out, and then this 1 cos alpha will go into one term of that cos squared alpha. So you have sine alpha over cos alpha. But that is equal to tan alpha, which is the left-hand side. So we've successfully proven mathematically that this identity holds true for when it is defined on its proper values, so the ones that are not the restrictions over here. All right, that's how we would do this type of question. I'll see you in the next one.